Hello, this is Jeff Badge of the Grinding Dock, and this is going to be a short video to explain what the hell does UPR mean, undulations per rev. And when people do a roundness profile like this, they'll do just a standard roundness profile, and they'll say, okay, how many undulations per rev do you have? And what undulations per rev distribution do you have? And it's something similar to a Fourier transform where we convert from time series to frequency series. Here we're converting from distance around the circumference series to a frequency, and that frequency is undulations per rev. So let's take it one step at a time and see if we can make sense of this. So here is a roundness profile. There it is, looks all right, looks good. But something's going on there. There's some kind of frequency that maybe is repeating itself. Okay, and what is that frequency? So there was a guy named Mr. Fourier who lived from 1768 to 1830. He did FFTs, other stuff. And let's see what Mr. Fourier came up with. And if you go to Wikipedia, you'll see something like this. And it's actually pretty good at representing all these sine waves as various frequencies. So let's say my wheel is going at 3,000 RPM and my workpiece is going at 150 RPM. 3,000 divided by 150 is 20.0000000. Every time the workpiece makes one revolution, the wheel makes 20 revolutions. So if I have a high point on my wheel, or an imbalanced wheel, or something funky in the wheel, I'm going to have that funkiness repeat itself 20 times per revolution of the workpiece, and I'm going to get boom, 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 20 high spots around the workpiece. Now that's the most simple case scenario, but it gets more complicated. So let's take it one at a time. Let's say you have a perfectly round workpiece. Perfect, no waves, no nothing. It is fabulously perfectly round. Your FFT, or your undulations per rev, will look like this. There will be nothing to see. Okay? So far, so good. Now let's say you have 20 waves on the workpiece, but they're perfect. There's 20 sine waves around the circumference of the workpiece. There's no phase shift between them. There's 20 perfect waves. You will get an amplitude versus UPR, undulations per rev, frequency FFT plot that looks exactly like that. You'll have one peak. It'll be 1 micron high because that's how big the wave is, your sine wave is. The amplitude is 1 micron up, 1 micron down for a total amplitude of 2 microns. So we're going to represent that as a perfect sine wave with an amplitude of 1 micron and a frequency of 20 waves per revolution of the workpiece. Okay, let's go to the next step. Let's say things are just a little bit weird though. Let's say I've got 20 waves, but those 20 waves are a little bit bigger over here, a little smaller over here, a little bit closer together in a certain spot, a little bit further away in a different spot. There's still pretty much 20 undulations per rev, but the spacing in a given section of the workpiece is not quite perfect. So what we get is something like that. Kind of a little mountain form. Okay, now let's make things more complicated. Let's say I have 2 undulations. So basically I just have a big egg. I've got 2 undulations on there. It's going to look like that. I'm going to have a big peak at 2 undulations per rev. Let's make things more complicated. What if I have 3 undulations per rev, and I have 20 undulations per rev superimposed over those 3. So I've got 3 undulations per rev. There it is. There's my 3 peaks per rev. But then superimposed on that, I have my 20 undulations per rev. So now I've got 3 and 20. So I have a peak of 1 micron at 3, and I have a peak of 1 micron at 20. But I still have a very predictable FFT, a very predictable undulations per rev graph. Now let's say I have this all by itself. I've got a perfect circle, but in there I have 95 25 undulations per rev. Looks just like that. So now my FFT undulations per rev graph is going to have one peak and only one peak right there at 95. Let's make it a little more complicated. Well, what if I have the 3, which I had before, and then superimposed on that, I've got the 20, which we saw before, and then superimposed on that, I've got 95. Well, now I've got a peak of 3 because I see those 3 lobes, and I see a peak of 20 because I've got those 20, and then superimposed on those, I've got 95, and I get a funky little shape that looks like that. Still a pretty simple FFT graph, but that's what it looks like. Okay, now let's make it even messier. This is a real life one, I believe. The ones up here I just made up for my explanation purposes, but this one here is a real one. So right here we see some kind of pattern that's pretty strong that's repeating itself. Boom, 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 boom. I'm guessing that lies around 60 to 70. So let's say 63 undulations per rev is the dominant one. But in addition, there's just some other little small weird stuff that might be noise or might be something meaningful that's occurring at these other frequencies. But they're just not that obvious. The obvious one is this one. And therefore we see that obvious one right there at 63. Let's take a look at another one. Here's a real profile that I pulled off of a real measurement. And here's what it looks like. Here's what my FFT is. That's a messy FFT. There's no dominant frequencies. This guy might be the biggest one at 30. Maybe I'll see something like that. But I also see these other little small ones. But none of them really stand out as being that strong and that dominant. So now we have an FFT that's messy. And if we're dissatisfied with this waviness profile, it's going to be more difficult to track down the cause of it. If we've got a waviness profile that looks like this, we can probably find the cause. Something's going on at 20 undulations per rev. And if we know the RPM of the workpiece, then we know what the frequency is in bounces or bangs per second or bounces per bangs per minute or RPM. So we can probably figure it out. So that's something real. Now we can get funky, and here I'm being imaginary again, where we get something like this, kind of a weird shape, and we get the sawtooth pattern. Or here's another real one. Here's an actual profile. I didn't make this one up. There's a dominant frequency around 25 undulations per rev. And in the chatter section of the book, I'd show you how to translate the 25 undulations per rev to a frequency in revolutions per minute or bounces per second or bangs per second or some bad thing happening per second. All you need is the workpiece RPM when it occurred. So now we're getting somewhere. So now it looks like we've got something that's going on at around 25 per second. Okay? And if you want to get weird, you can create funky patterns. This is all theoretical though. So I just did this messing around. And this is what they show on Wikipedia. So that is how the undulations per rev FFT Fourier transform thing works. Basically, we're just saying, what are the frequencies of the waves that we have on our workpiece? And this is Jeff Badge of the Grinding Doc talking about waves on the workpiece, which you get in cylindrical grinding, centerless grinding too, and that helps us track down what the cause of the problem is and how we deal with it. This is the stuff you get in the Book of Grinding. This is the stuff I teach in my course. Don't reinvent the wheel. Don't just go with trial and error. Don't beat your head against the wall hoping for a solution. Learn the science of grinding, and life will just be easier. You'll produce more parts. You'll produce less scrap. Your cycle times will be lower. You'll just do better if you understand grinding. Attend one of my grinding courses, www.thegrindingdoc.com.